the group itself is an abstract thing, and only thing that group has to satisfy its multiplication table.
Okay.
It's defined by its multiplication table, and anything that has that multiplication table is said to be isomorphic, meaning it can be described by that group. So we use, in the case of the three objects, we have three intuitions from our life. One is I take 3 balls, or, label 1 to 3 or 3 colors, and I'm asked to produce all possible arrangements of 3 balls which are different, which is, 6 of them, 3 factorial. The other one is I take a triangle and I rotate it and flip it. Turns out also 6. So they're isomorphic. But then we give you other examples. One example that is kind of obvious, we're in a plane. So every time you make rotation by 1/3, you can write a matrix with sines and cosines, and then when you evaluate it, that's kind of square roots of 3s, etc., that show up. So that's a 2-dimensional matrix representation. That one is not permutation representation of, just interchanging objects. It's not a matrix that takes 3 objects or, does something to them by zeros and 1. It's 2-dimensional matrix, which is implementing 3-dimension, what in our notion should be 3 objects. And now to make it a little bit more, perfidious, but shows up in application, we give you this example where we take 2-dimensional complex matrix. And the only thing you always have to do to solve these problems is you just have to verify that if you multiply them out and write out the table, that table is the same as the multiplication table for, S3 permutation group. That's all.
So it would look like the 3x3 matrix of those 3 matrices that are given, seeing how they multiply out and making sure that it's all
just multiply. It's very easy, and basically if they fall into classes. There are 3 kinds of matrices you get.